All right, so there's a couple of things that we've learned in the past chapter that this chapter is based on, and you sort of saw some of this last chapter. Okay. Okay, so what we learned was if you have a current like this, it produces a magnetic field like that. Okay, so the magnetic field lines are circular, and the magnetic field at any location would be tangent to this circular field lines. Okay, so you saw that. Now you also saw that if you have a loop of wire, and if the magnetic field is changing, so for instance, if the magnetic field increases, that will induce an electric field in this direction. And if there was a wire there, it could induce a current in the wire. Okay, so you saw that. Now let's combine the two ideas. Okay, now here's the deal, going back to this. Now let's say let's say in this diagram, if the current changes direction, okay, when the current is in that direction, the magnetic field is like this. And when the current switches direction, the magnetic field is like that, okay? And you see that anytime you change magnetic fields, you can induce a current in a neighboring wire, okay? So let's imagine the following. So this is an AC source, which we'll actually talk about in the next chapter. But anyway, so here's a circuit. So here's a circuit with an AC source. So the current is a function of time. And let's say here's a nearby circuit. Okay. Now this changing current will induce a magnetic field, dB by dt in this circuit, which will induce a current. Okay. So in this nearby circuit, just because of changes happening in this circuit, you're inducing a current. Okay, so that's an induced current. Okay. And maybe the circuit didn't want that current. Okay, it could adversely affect this circuit. And in fact, this happens. So, for instance, if you have a large factory floor, and so you have to protect against this. So here is this machine running, and then you turn on this machine. Now the current in this machine change, and that will induce a current here, and maybe there's a safety feature in here that'll turn off this machine because of this spurious current. Okay, so imagine this large factory floor, you got multiple machines working, and this got turned on and these machines got shut off, and you wouldn't want that. So anyway, so stuff like that happens, and so that's what this chapter is about. This is called mutual inductance. Changes of currents in this circuit are influencing nearby circuits. And nowadays, you know, we all can't live without microchips. There are multiple, large number of circuits within a small chip in close proximity. So you have to know about, you have to learn about this stuff. Okay, so that was the motivational part for this chapter. Now let's go through the slides. So the chapter is inductance. Okay, so what this is showing you is, so here's coil 1, and there's a current passing through this coil 1, and let's say if the current changes in this coil, it will induce a current in this secondary coil. Okay, so often magnetic flux through a circuit changes because of time varying currents in nearby circuits. So the magnetic flux in this circuit change because of time varying currents in this circuit. Mutual inductance can be a nuisance in electrical circuits, since variation of current in one circuit can induce unwanted EMFs in nearby circuits. Okay, so this guy is being influenced just because of the proximity to this circuit. Okay, so, and we'll learn about transformers. That's one of the most important applications that we use in our everyday life. Okay. So here's how we define mutual inductance. Okay, so mutual inductance between these two circuits. Okay, the EMF induced in circuit 2 because of changes in current in circuit 1. Okay, so currents are changing in circuit 1, and that is inducing us EMF in circuit 2. Okay, and that proportionality constant is called the mutual inductance. Okay, now this guy is hard to calculate for arbitrary circuits. So for instance, let's see, let's make sure you understand this. So this is 2, 1, EMF induced in circuit 2 is M1, 2, di1 by dt. Okay, now M1, 2 for the same two circuits has changed now. So this M1, 2 prime is not equal to this M1, 2. Did you guys understand that? So it depends on the configuration of the system, depends on the distance between the circuits and all that stuff. And so M12 is really hard to calculate. You just have to experimentally figure it out. So that's what that is. Okay, so it's a proportionality constant. And it tells you what is the induced EMF in circuit 2 when you're changing currents in circuit 1. All right, now can anybody tell me the following? So let's make sure we understand this. So you change the current in this circuit. Oops. All right, so you change the current in this circuit, and EMF was induced in this circuit. Okay, now you do the same di by dt here. Is the EMF induced in this circuit larger or smaller? Let's, can I unmute your microphones, and can anybody answer that? So in this circuit, when we're further apart, is the induced EMF going to be larger or smaller in this circuit? Anybody? Okay. So I hope you guys understand that the induced EMF will be smaller in this circuit. Okay. So so that's what the mutual inductance is. Again, this is hard to calculate for arbitrary circuits like that. We will calculate it for some special configurations. All right, now let's talk about self-inductance. So this is interesting. So let's see. Now, let's say you have a straight piece of wire. Okay. And if you increase the voltage, the current will increase. Okay. You guys have all seen batteries in a lab where you can increase the voltage by turning the dial. And what that does is it'll increase the current in the resistor. Now, so this resistor can be thought of as made up from a straight piece of wire. Now, if you take the straight piece of wire, any straight piece of wire, and wind it into a solenoid like this. Okay, so you're winding it into a spiral. And now if you connect it to a battery, okay, now if you increase the voltage, the current doesn't increase instantaneously. What this straight piece of wire, when wound like that, acquires a property where it will induce an EMF in the opposite direction. So if you're trying to increase the current, it's fighting the your need to increase the current. So a piece of wire, when wound up like a solenoid, acquires a property of fighting changes in currents. So it fights changes in currents. Okay, so if you try to decrease, so similarly, if you, from this loop of wire, if you try to decrease the voltage and try to decrease the current, what this will do is it'll fight that, and EMF will be induced in this direction. Okay, and the EMF is induced as long as the current is changing. If the current is steady, this EMF is not induced anymore. Okay, so so that's what this slide is showing you. So in this, so there is this solenoid, and here's a steady current. Now, if you try and increase the current, and EMF is induced in this this solenoid in the opposite direction. Okay, and if you try and, so if you try and increase the current, the EMF induced will try and push an opposing current opposing this thing. If you try and decrease the current, the EMF is induced in that direction to keep this current steady. Okay, and this is the self-inductance of this coil of wire. Okay, so if you take this coil of wire and make it into a straight wire, its self-inductance will go to 0, meaning it cannot induce an EMF. Okay, so the same wire, you just make it straight and it won't be able to do this anymore. Okay, its self-inductance will be 0. Okay, so an opposing self-induced EMF develops as current increases or decreases in an inductor. The self-induced EMF is proportional to time rate of change of the current in the inductor. What this is saying is, if if you change the current faster, this EMF will be larger. Okay, so that's what that means. Okay, so what this diagram shows you is, if you have a loop wire that you looped into a solenoid, if you try and increase the current in this direction, the induced EMF will be in that direction. And if the current was flowing in that direction and you try to decrease the current, the induced EMF will be in that direction. Okay. So induced EMF opposes decrease, and induced EMF opposes increase. So the induced EMF is opposing change, is what it's doing. All right, so now the self-inductance for a closely wound solenoid, of N turns, the inductance can be given. The inductance, so by the way, so the for a closely wound solenoid, if the current is increasing, this induced EMF is given by this expression. It's minus L times di by dt. L is called the inductance of the coil, and the inductance is given by this expression. Mu naught, little n is the number of turns per unit length. A is the area of cross-section of the coil, and L is the length of the coil. This is the volume of the coil. Okay, so let's make sure. So for a solenoid, L, the self-inductance is mu naught N. N is number of turns per unit length. Okay. And L is the length of the coil, and A is the area of cross-section. Okay. So that's the self-inductance. And again, if you take this wire, make it into a straight wire, now its self-inductance is 0. Okay. All right, so what does the self-inductance tell you? It's the proportionality constant. It tells you how large will the EMF be as you try and change the current. Okay. The units of self-inductance are EMF is measured in volts, volts second divided by amp. So volts times second divided by amp. So the units of L are volts second divided by amps. So again, for solenoids, there's the self-inductance. Okay, so what this expression is telling you is if you fill it with a magnetic material, so self-inductance is a useful property. Okay, self-inductance is a useful property. So this is the self-inductance for an air-filled inductor, and sometimes you're interested in large self-inductance. So what you do is you fill it with a magnetic material, a magnet, and the self-inductance becomes mu m n square al, where mu m is mu naught times a constant. Okay. Okay, I forget the standard notation for this constant, but so mu m by mu naught is much greater than 1. Well, I mean, you can make it much greater than 1 for magnetic materials. So you can increase the self-inductance of a solenoid. Okay, so that's mu m. That's all right. So now we'll look at what when if you introduce an inductance in a circuit, what will it do? Okay, so that's what we're going to do now next. So here's the deal. All right, so if you have just a resistor in a circuit, and here's a switch, okay, and let's say you close the switch at t equal to 0. The current before negative t's will be 0, and when the instant you close the switch, the current will go to its maximum value E by R and remain steady. Okay, when you close the switch. Now here's the funny thing that happens. If you place an inductor, add an inductor. Okay. Now if you add an inductor and do the same thing, you close the switch, and at t equal to 0, you close the switch for negative times, the current was 0. And now instead of rising instantaneously, the current rises exponentially and goes to the steady state value of E over R. Okay, so this inductor has changed the behavior of the circuit by fighting the rise in current. Okay, so that's what we'll see. All right, so let me show you this simulation. Okay, so here's the resistor, here's the battery, and here's the inductor. Okay, I'll close the switch, and you see the current is not instantaneously rising, but it rises exponentially. Okay. And so what we are interested in finding I as a function of time. Okay, so that's what we're going to look at in the next few slides. Okay, so we are going to look at how the current changes with time in this circuit. Okay. So what we are interested in is so in this circuit, coming back to this circuit, so we are interested in I as a function of time. All right, I will pause recording right now, and